Good afternoon. So I'd like to start by thanking the organizers for this opportunity. Florence is my favorite place to visit. So today I'll be talking about negativity, entanglement negativity, which is related to the operation called partial transpose, and I will be talking about systems of fermions. And as some sort of bonus, we can also talk about topological phases of fermions. Okay, so much of this. So we've been working on this subject for last few years, and it's in collaboration with my student Hassan and postdoc Ken. So Hassan is in the audience. So Ken is now in Japan as a postdoc. Okay, so the plan is okay. So here's a quick summary I already said, but so I will be talking about fermionic systems, and for fermionic systems. As it turns out, the notion of partial transpose has to be properly introduced. So we constructed this partial transpose operation for fermionic systems, and we check the validity of this operation. And then I will talk about application of this new operation, fermionic version of partial transpose, to understand the quantum entanglement of fermionic systems and the topological phases of fermions. So obviously, I will start with partial transpose and the negativities in bosonic systems. And so I will explain what it is and why it is useful. But then I will switch over to fermionic systems. Okay. So first of all, what is partial transpose? The setting is that we have a bipartite Hilbert space. So total Hilbert space can have a tensor factorization HA1 and HA2. So you take some basis. So this is the matrix element of your operator. In particular, I'll be talking about density operators. So these are bases for this tensor Hilbert space. Okay. But then I will take the transpose, so which means we exchange row and the column. But by partial, I mean I do that only for subsystem, one of the subsystems here, let's say for subsystem A2. So if you look at these matrix elements, if I have a partially transposed density matrix, the entries for the second Hilbert space are switched. Okay, so that's a definition of partial transpose. Okay, so question is why we are interested in doing this. By taking some examples, I will try to illustrate how this is useful. So in particular, this operation is useful because you can detect some sort of quantum correlation or quantum entanglement. More explicitly, we can define a quantities which we call entanglement negativity, and log version of it, and that's why useful. Another aspect which may be more relevant to the discussion of topological phases, you should think of this operation partial transpose as some sort of partial time reversal. So in quantum mechanics, time reversal is anti-unitary, so you have to take a complex conjugation. Acting on the Hamiltonian, since it's a Hermitian, taking the complex conjugation is equal to taking the transpose. So this operation, maybe you can also see from the fact that I exchange input index and output index. So we are kind of reversing the arrow of time. So that's what this transpose does. And as it turns out, this is useful when we discuss topological phases in the presence of time reversal symmetry. But first, let's just take a look at this simplest example, which is the bell pair. So I have 2 qubits, and to simplify discussion, I just take a pure state. Okay, pure state is sort of too simple, but it's to illustrate the usefulness of partial transpose. So for this pure state, if I write out density matrix, it looks like this. But now we take a partial transpose. So if you look at these matrix elements here, taking partial transpose doesn't do anything. But for the last 2 terms, essentially you turn these terms into this term. Okay. So what we are interested in now is that what happens as you take partial transpose, what happens to your density matrix. Okay. Intuitively, if your state has no correlations between first and second qubit, taking partial transpose wouldn't do much. Okay. But if 2 degrees of freedom are very strongly correlated, taking partial transpose may have a dramatic effect. By dramatic effect here, I mean that if you look at the spectrum of the partially transposed density matrix, it's not a positive anymore. So some negative eigenvalue appears, which is signaling the original correlation in the original system. So it's like you're twisting your arm, and since your arm is connected to your body, and then to the other hands, you feel something. But if okay, we don't have to say that anymore. But anyway, so that's the idea. So because of the correlations, your density matrix changes dramatically. In particular, negative eigenvalues appears. So that's the idea of positive partial transpose criterion for the separability conditions. And if a negative eigenvalues appears, it means it's not separable. Here I did this for a pure state, but for pure state, entanglement entropy for Neumann entropy is already a perfect, very well defined, very well suited entanglement measure. So for that case, you may not want to look at negativity or partial transpose, but the advantage of considering partial transpose really comes up if you start thinking about mixed states, entanglement in mixed states. So for Neumann entropy is not the good quantum, not a good entanglement measure for mixed state. It is it doesn't uniformly decrease under LHC operations, but entanglement and negativity, as it turns out, it's a good quantum entanglement measure for mixed state. So that is the motivation to think about entanglement negativity and partial transpose. So yeah, we're thinking about a mixed state. Okay. So that's the kind of virtue of considering partial transpose in the context of quantum entanglement. And as it turns out, it's also useful to discuss correlated phases, like topological phases of matter in condensed matter. So I want to take another example to illustrate this point. And the canonical example is the Haldane phase. So that is realized in, for example, spin 1 antiferromagnetic Heisenberg model. And this model is known to be, the ground state of this model to be known to be gapped, and there is no spontaneous symmetry breaking. And as it turns out, it is an example of a topological phase, or in terms of more technical term, it's a topological phase protected by symmetry. So it's a trivial phase in the sense that if you don't impose any symmetry, you can basically continuously or adiabatically turn the Haldane phase into simple product state. But you cannot do this in the presence of some symmetry. For example, if you have a time reversal symmetry, if you impose time reversal symmetry, Haldane phase is sharply separated from trivial product state in the sense that there's no path, no adiabatic path connecting Haldane phase and the product state. Okay. Nice way to picturize the ground state of the Haldane chain is to draw this picture. So you have a this is my lattice, one-dimensional lattice, and at each site I have a spin 1 degrees of freedom. But you can sort of virtually break spin 1 into 2 spin 1/2 degrees of freedom, and then in the ground state of the Haldane phase, the virtual spin 1/2 form a pairs, not within this original site, but they form a pair across the site. Okay, so this is the ground state of the, more or less the ground state of the Haldane phase. This is the correlated entangled state in the sense that if you try to make a boundary to the system, what you cannot avoid is that you effectively cut this Bell pair somewhere. So then there's this effective 1/2 degrees of freedom appearing on the boundary. Okay, so that's kind of that's signaling the non-trivial topology of the Haldane phase. Okay, so this is a well-known story. But I guess what is less well known is that the partial transpose operation is very useful to characterize the topology of this ground state, which may be also already perhaps kind of evident because each of these blue partial bonds are Bell pairs, and we just studied the Bell pair, and then we said for Bell pairs, partial transpose is very useful. But let me say more about the usefulness of the partial transpose. So in particular, by making use of partial transpose, as it turns out, we can define topological invariant of the Haldane chain. So by topological invariant, I mean a quantized quantity which takes the single value for a given phase. So you start from some ground state, gap ground state. You can move within this phase, but topological, if there's a topological invariant, it doesn't change at all. So it's like a version of order parameter for topological phases. Here there's no spontaneous symmetry breaking, so we cannot use order parameters and the Randall-Ginsburg type of theory to characterize such topological phases, but something like topological invariants may exist, and then they can be used to characterize topological phases. Okay, so but since Haldane phase is a topological phase protected by time reversal symmetry, we have to somehow input this fact. Time reversal symmetry is necessary. And then, as it turns out, this partial transpose is a very good way to make use of time reversal symmetry to define topological invariant. So here's a procedure which is according to Pullman and Turner. So I start from one-dimensional lattice, okay, and I have a ground state. And for the sake of simplicity, I assume it's just very large or infinitely large. And then I cut out a finite region, finite segment I of some length. This is somewhat arbitrary, but it has to be just larger than the bulk correlation length. So that's step one. So I define my reduced density matrix for this given region, which is in the mixed state. Now I subdivide this interval into two subintervals, I1 and I2. Okay. So then we have a setup which is a setup which is perfect for negativity. But I don't compute negativity now, but I will define topological invariant. So then, for this bipartite subspace defined for these two intervals, which are adjacent to each other, I take a partial transpose, let's say for I1, and I define partially transposed reduced density matrix. So the final step is to take this combination of the original and partially transposed density matrices and take a trace, okay? Which is rather similar to negativity, but unlike negativity, I mix original density matrix and partial transpose matrix. As it turns out, the phase of this quantity is topological invariant. Pullman and Turner use the matrix product representation of the ground state to reach this conclusion. I want to sketch this construction a little bit. So if I write out my ground state by using matrix product state, so I have some matrices and I have these physical and the virtual indices, and then you can develop matrix product state representation of this quantity. So ground state have one, let's say this is ground state. So to form a density matrix, I need this one together with its conjugate. I have now two lines, but I have now a partially transposed density matrix. So I need 4 horizontal lines in total, but then I have to connect them. So outside of the interval I just connect this way, and nothing really interesting happens there. But in this region, interval I have I multiply density matrices, so I connect these indices, and for I1 and I2, taking partial transpose means I connect these indices differently, which for I2. Okay. For me, the essential insight why this quantity ever gives you something like topological invariant comes from the fact that if you look at this diagram long enough, maybe week or something like that, what you realize is that you can deform so you can look at this, think of this as a matrix product state as some sort of discrete path integral, and then you can deform your path integral. It's a topological phase, so in some sense there's a lot of flexibility of adiabatically deforming your space-time manifold. But then in the end, what you realize is that this matrix product state discrete version of path integral is really the path integral defined on the unoriented space-time, which is in this case it's a real projective plane. And like I said, it takes a week to realize this, so I don't convince you now, but just believe me. So it's a path integral defined on the real projective plane. This is the what is expected from topological quantum field theory description of Haldane chain. Okay, so this Pullman-Turner invariant, which perhaps they didn't realize at that time, but it is really the matrix product state representation of the path integral on the real projective plane, and topological quantum field theory says it's -1 on real projective plane, and it's topological. Okay, I will come back to this point more for the case of fermions, but just for now, I'm just reviewing what's known for bosonic cases. Okay, so, yes? Yeah, so you're talking about the size of this interval? Yes, so in fact, in this representation, yes, it can be very small. So you can actually compute this invariant analytically. But if you are not at this ideal point in the phase diagram, the size of this subsystem has to be bigger than bulk correlation length. Yeah. yeah, there's some constraint, yes. But yeah, but you're right. It can be very small in topological systems. So it's actually relatively easy to compute. Okay, right. So yeah, so this is summary so far. So partial transpose is a useful tool to diagnose entanglement and the topology of quantum many-body wave functions. And I want to basically uplift this success to cases of fermions. Okay, so the model system could be something like a one-dimensional Kita-F chain, which is kind of type of system Ian described on Monday, except this is much simpler. It's a 1D system. So it's a one-dimensional chain, and instead of spins, we now have fermions hopping on the lattice. And this model realizes a version of a topological phase, which is a topological superconductor phase. In particular, if this hopping and the pairing potential is bigger than the chemical potential. So sociologically, this is the phase of much interest now, because it can realize, it is experimentally realized that it can host Majorana fermions on the boundary, and it can be used to some interesting quantum information purposes. Okay. Once again, this ground state of this model can be visualized by this diagram, which is again very similar to the Haldane chain. So in this case, we break up a physical fermion or electron. In this case, it's spinless. In this model, it's a spinless fermion. But we split this fermion operator into two real fermion operators, and we form a pair, not within the site, but we form an inter-site pair of these Majorana fermions, and that's the kind of graphical representation of the ground state of the Kita-F chain, if it is in the topological phase. Okay, so then this is a kind of example of topological phase of fermion, and it has entanglement as well. So can we use the same idea, meaning can we use partial transpose to discuss entanglement and topology of the Kita-F chain? So now I want to point out some issues before I describe our construction of the partial transpose. So one naive thing we could try is to take fermion systems and the fermion ground state, but we can Jordan-Wigner transform, and then we can sort of embed our fermionic Hilbert space into bosonic Hilbert space. But since it now looks like a bosonic systems, we can try out the partial transpose operation, which we just defined for generic bosonic systems, and then just try out what happens. So here's the kind of sample calculation. We take a small Kita-F chain, and then I divide up my system just as before, and then we discuss, in this case, negativity of the Kita-F chain in the ground state. And then for now, I'd like to focus on this curve here, and ignore this curve for the moment. Okay. So this is the entanglement negativity defined for this configuration, and which is actually 0 deep inside topological superconductor phase. Okay. So that's of course somewhat mysterious if we remember the picture I just showed you. So that's the ground state forming a kind of inter-site pairing of Majorana operators, but here negativity somehow fails to capture that correlations. Okay, so that is the first issue I want to point out. So it seems like if I adopt the bosonic definition of partial transpose, it is incapable of capturing the fermionic correlations. So what's happening here is the following. So we are somehow embedding fermion Hilbert space into bosonic Hilbert space, and we use the bosonic entanglement measure. But to get the fermionic ground state, or fermionic, meaningful fermionic state, what you shouldn't forget is the fact that fermion Hilbert space is naturally graded in terms of fermion number parity operations. Okay? So, so what bosonic entanglement measure thinks entangled is actually not allowed in fermionic. They are not allowed as a fermionic state, because usually they are the superposition of fermion number parity even and fermion number parity even and odd parts, they are mixed. But once you say your system is actually fermions, you have to be definite about fermion number parity, and essentially entanglement is then killed completely. The entanglement which is captured by negativity is essentially just killed. Okay. But on the other hand, we of course think that something like a topological superconductor phase is entangled. It has a quantum correlation. So it seems like we have to somehow come up with a better way to diagnose the entanglement in the Kita-F chain. So that's issue one. The second issue is somewhat technical, but it's somewhat, once again, mysterious. So for bosonic systems, you can talk about the simple examples of bosonic states, for example, Gaussian states. They are for example, the ground state of free bosonic systems, eigenstate of free bosonic systems. So then, after taking partial transpose, Gaussian state remain Gaussian for bosonic systems. Okay, so technically it means you can compute negativity very easily for bosonic systems. Whereas if I once again adopt bosonic definition of partial transpose, even if you start from fermionic Gaussian state, state will not stay Gaussian after you take a partial transpose. So it will be, after you take a partial transpose, you get the fermion number parity odd and fermion number parity even part. They are mixed. Each of them can, as it turns out, each of them are Gaussian, but as a total, they are not a Gaussian state, which means computing entanglement negativity is mysteriously difficult even for free fermion systems. Okay, so that's some technical point, but nevertheless, it's a mysterious point. Okay, so now, so then we went back to the definition of the partial transpose, and then we thought it may be not the optimal definition, in particular because it doesn't capture the type of correlation we want to capture. So the basic strategy now we took was the following. So to decide on the optimal definition of the fermionic partial transpose, if it exists, we first look at the topological invariant. Okay. So the lesson we learned from the bosonic example, the Haldane chain, we should be able to use partial transpose, some sort of partial transpose operation to define topological invariant. We should have the ability to change the space-time topology such that you should be able to get space-time manifold which is unorientable. Okay, so we assume there should be such a operation that exists because we expect that topological superconductor phase is described by some sort of topological quantum field theory. So basically, we try to match the results from topological quantum field theory and microscopic definition of fermionic partial transpose. Okay. So once we do that, we take this as a definition of the fermionic partial transpose. Then we can use it to discuss phases away from the topological limit, maybe even at the critical point, and also in addition to topological invariant, we can also discuss quantum entanglement, like a negativity and so on and so forth. So sort of additional ingredient as compared to the bosonic case is the fact that fermionic systems sort of remembers or must be dependent on the additional data of the space-time, which is called spin structures or pin structures. So we have to, if microscopic definition of the partial transpose, if it exists, it must implement correct pin structure or spin structures. So that's our basic strategy. Okay, but it's a little bit, sorry, there are a lot of sentences without any equations, but so if you're interested, I can describe this more. But let me now, move on to the our definition of partial transpose. We can also take a coherent state basis, or we can use this basis. So let me use this operator basis to explain our definition. So we first expand our operator in terms of as a polynomial of fermion operators. So some of them are living in this first part of the Hilbert space, or they're acting on the first part of the Hilbert space, and there are the remaining operators are acting on the other part of the Hilbert space. So you can separate them out. If you expand, then you can separate them out, and there's some coefficient. Okay, so partial transpose operation acts only half of it, this part of it, and what it does is to produce this phase. Okay, so this phase turns out to be very crucial to reproduce, to capture the quantum correlations and also topological invariant. After we completed this work, we were also informed from matrix product states community that the fermionic version of the matrix product states, and from that point of view, also adding this phase is very natural. Okay, but anyway, we take now we have a modified definition, if we wish, the partial transpose. Now we can test this definition. Okay, so first thing is that we now look at this. It's the same picture as before, but now we look at this curve. And this curve is now, once again, it's a negativity, but now defined with respect to our definition of partial transpose. And now it's non-zero in topological phase. And as you move towards trivial phase, it starts to decrease. Okay? So that's more reasonable behavior. So that's good. And also, this is the critical point separating these two phases, which is a conformal field theory with center charge 1/2. So if you look at the negativity at this critical point, we reproduce the expected result from conformal field theory, which is fitted by this formula. So maybe I shouldn't say that, but as a bonus of this definition, as it turns out, our Gaussian state, stay Gaussian, even after taking partial transpose. So for example, for Kita F chain, which is a free fermion chain, computing negativity is actually very easy. So these points, for example, you can get from numerics, and it matches perfectly with the CFT result. We can also actually do analytic computation of the negativity, and it also matches with the CFT result. Okay, so that's the first thing I want to, for the entanglement, our definition seems to work perfectly. Now for the topological invariant, we can now, topological invariant using our partial transpose. So we take the same setup as before, but we just use fermionic version of partial transpose. Then we compute the topological invariant, and as this graph. So we are moving on this axis. We have a different parameter. So we are moving in the phase diagram, and we plot the this topological invariant, which shows the perfect quantization. The interesting feature is that unlike bosonic case, this quantity, the phase of this quantity, is quantized to be eighth root of unity. So Haldane phase is a Z2 in the sense that topological invariant takes only 2 values, but here topological invariant can take 8 possible values, which is consistent with known classification of 1D Majorana fermion chain with time reversal symmetry. So not just entanglement, but for topological properties, our partial transpose works very well. Yeah, so I want to say two more things. We have defined entanglement negativity using our fermionic version of our partial transpose. But then there's a question. So original entanglement negativity is a good, I said it's a good quantum entanglement measure, which means it uniformly, monotonically decreases under LHC operations. But we define new quantity. So is it actually good quantum entanglement measure? So we visited this problem in our recent paper, where we show that our fermionic version of entanglement negativity is in fact is a monotonical decrease under LHC operation if we limit our LHC operation to be consistent with fermion number parity conservation. So you don't mix different sectors with different fermion number parities, but so far as we agree on this LHC, fermionic version of LHC, fermionic version of negativity monotonically decreases. So it's a good entanglement measure in that sense. Okay, the second application is the final point is that beyond the Kita F chain, we can also discuss other topological phases protected by time reversal symmetry. So I think the most famous one would be just a topological insulator, let's say in 2 dimension, which is the topological phase protected by time reversal and particle number conservation, U1. Okay, and historically, this subject has been discussed quite extensively, but usually we use free fermion band theory picture, and we build topological invariant using free fermion block wave functions. But now with this understanding, the exercise we did for 1D, we can now formulate topological invariant for topological insulators in free many-body way. Okay, so I just want to flash you our formula for many-body Z2 topological invariant. So setup is now 2 dimensions. So I'm taking a cylinder, and as before, I partition my regions. Now we have 3 regions: region 1, region 2, and the outside of these regions. And then the proposed topological invariant is this. And if I unpack the definition here a little bit, it's very similar. If you just look at this part, and if you ignore something in between, it's a density matrix for these 2 regions multiplied by a partially transposed density matrix for these regions and take a trace. But since charge U1 is also conserved, we also have to do something with this aspect. So we have to put U1 phase twist when we define the density matrix, but then we take a partial transpose. So I would say it's very similar to one-dimensional case. And we tested this topological invariant on the lattice, some model, and then it shows a Z2 quantization. So this is this works as a topological invariant for topological insulator, and it's fully many-body. There's no reference to single particle states at all. Okay, with that, I want to conclude. So we did constructed fermionic version of partial transpose, and we can make use of that to discuss entanglement and the topology in fermionic many-body system. So that's all. Yeah, thank you for your attention.
Yes, thank you. So if you are thinking of putting on the same phase diagram the entanglement entropy, I think that they would have a strong peak at the phase transition because, well, that's the only place where the entanglement entropy violates the area law. So whereas here you seem to have something which is not necessarily very strong at the quantum phase transition, which are singles out the topological phase. Do you have a way to reconcile, or do you expect maybe that there is a singularity
Yes.
at the critical point as well?
Yeah, so thank you for pointing this out. So I didn't say perhaps clearly, but this is for just 8 sides chain.
Yes.
So as you increase your system size, there will be a peak here. And the peak is, of course, peak gets bigger as you increase your system size, which the increase is fit by this formula.
All right. Oh,
So it's so sorry, the picture was sort of was deceiving,
yes.
but the same peak, you see the same kind of peak
Yes.
for negativity.
And a very short question is, well, if you turn on the temperature now on top of the topological phase, do you think that any indication of the topological invariant will survive, or it just gradually washed out as you increase T?
Yeah, so that's a very good question. So we have an unpublished work which we are writing up now. So we did study temperature dependence, and roughly speaking, yeah, we can talk later, but yeah, as you increase temperature, topological, non-trivial topological invariant eventually goes away, and we sort of understand why.
All right, next question.
Okay, I'm sure you get this question a lot, but can you define these quantities for gauge theories or in case of non-factorizable Hilbert spaces?
Oh. Yeah, you got me. I have to think about it. That's a very interesting question. But yeah, maybe we can talk later. Yeah.
Okay, more questions? Okay.
Yes. So this is this topological insulator which has a spin. So, but then you have to add spin flip. So take a transpose, but to adopt this physical time reversal, you also want to flip, spin.
Yes. In the bosonic case, you said that this topological quantity is related to partition function on projective space. In the fermionic case, do you have something similar?
Yes. So yeah, exactly. So for topological invariant story, we always look for, almost all cases, we look for unoriented spacetime manifolds. That's what we want to realize by taking this topological invariant. The precise which unoriented manifold is, we have to work this out. But for Kitaev chain, yes, it's still a real projective plane. For topological insulator, it's a Klein bottle times S1. So it's unoriented, but it's a different spacetime manifold.
Okay, yeah. So for what you call bosonic partial transpose, it's known that it is just a sufficient condition for entanglement. So if it is non-zero, then the entanglement, then the state is entangled. In this new definition, is also a necessary condition or not?
Yeah. So generic answer, we don't know, like in this bosonic case, but we studied kind of few fermion systems. Like we study 2 qubits, 3 qubit system, we studied 2 Majorana fermions, 3 Majorana fermions, and so on and so forth. And the for few fermion cases, we have something definite to say. That's the reason is simply because of the fermion parity conservation, we have somehow more limited to the form of the density matrices, but generic answer we don't know.